Welcome to AQA AS 8.2. You need to look at your textbook for this video. It's page 138 to 139. So our lesson objectives for today are to have a qualitative understanding of the Maxwell Boltzmann distribution of molecular energies in gases. Now, qualitative just means to do with a feel for how things rather than actually talking about numbers. You also need to be able to draw and interpret distribution curves for different temperatures. And you need to understand how small temperature increases can lead to a large increase in rate. So first of all, we need to look at what a Maxwell Boltzmann distribution is, and instead of trying to describe it, it's easier just to look at one. So here's an example of one. So a Maxwell Boltzmann distribution just shows the distribution of the energy amongst a given amount of molecules. So on the y-axis you have the number of molecules, and on the x-axis you have the energy. And on this graph, the area under the curve represents the total number of molecules. And you can see on there, I've drawn in the activation energy. So the activation energy, remember, is the amount of energy that the particles need if there's going to be a successful reaction. So therefore, you can see that vertical line representing the activation energy. All the molecules to the right hand side of that, which I've shaded in with green, they have the activation energy, so any of those will end up, if they collide, will lead to a successful reaction. Okay, so there's several important things about the Maxwell Boltzmann distribution curve, which I'll show you on the next slide. So first of all, the most probable energy is represented by the highest point on the curve. There's an arrow pointing to the highest point on the curve, and it's important to notice, although this is the most probable energy, it's not the average energy if we're using the average in the normal way we use it, which is the mean energy. So it's not the mean energy, it's the most probable energy, because it's got that's the highest number of molecules have got that energy. Okay, so secondly, as I said on the previous slide, the total number of particles is represented by the area under the curve. This becomes important later. And then there's two important things about how you draw the curve. So when you draw these in exams, you have to make sure, first of all, make sure your axes are labelled. So on the y-axis, number of molecules, on the x-axis, energy. Secondly, the curve has to go through 0, 0. And I've drawn an arrow to 0, 0 there to show that no particles have got 0 energy. So the line has to go through 0, 0, otherwise you will lose marks in an exam. And lastly, on the right hand side there's an arrow with a box saying that there's no upper limit to the energy. So what this means is that the curve does not reach the x-axis on the right hand side. So although it goes through 0, 0 on the left hand side, on the right hand side it never reaches the axes. And this is important when you're drawing it, because if you draw it touching the axes, then you will lose marks. So if you're drawing it, make sure it goes through 0, 0, and make sure it doesn't touch the x-axis again. Okay, so we can use the Maxwell Boltzmann distribution to explain what happens when we change the temperature of a reaction and why that leads to an increasing rate of reaction. So on the next slide, I'm going to show you. So I'm going to show you on this one. There's two lines there. Okay, so the first one is exactly the same as I had on the previous slide. So, as I said before, the total number of particles is represented by the area under the curve. So if we increase the temperature in a system, we're not changing the number of particles. So therefore the area under the curve has to stay the same. Okay, so you'll have to give me a bit of a leeway with my diagram here, because the area under it will not be exactly the same because I've just drawn it very roughly. But if you had a proper curve that was drawn correctly and accurately, then the area under the curve should be the same, even though you change the temperature. So when you increase the temperature, there's two lines there. The one that's to the left and higher is the original one. And then as we've increased the temperature, when you do that, the curve goes downwards and it goes to the right. So what you see is the top of the curve for the higher temperature is lower than the original one. And it's also gone to the right. So the the most probable energy. We said that that highest point was the most probable energy. The most probable energy is now higher than it was before. So when you're asked to do this in an exam and you're asked to show a curve representing an increase in temperature, make sure the curve goes downwards and it goes to the right. If you're asked to do the opposite, of course, if you're asked to show a decrease in temperature, then it would have to go left and it would have to go upwards. Okay, so on the previous slide I had shaded in green the area that represented the number of particles that had the activation energy. So we've still got this on this diagram, but now for the second curve that's got a higher temperature, I've shaded in yellow now the area under the curve to represent the particles or the molecules which have the activation energy in it. So now you can see the green area is that stayed the same. So you've still got those original particles that had the activation energy, so would lead to a successful reaction. But now you've got an extra area under the curve because the curve is to the right but above it. That means you've got an increase in the area under the curve for the part where the activation energy has been reached. So you can see on that there is roughly twice as many particles now that have the activation energy. Now one point I didn't mention about the curve, which is important, is that when you've drawn the second curve at higher temperature, then you have to make sure that on the right hand side that the line is above the original line. So do make sure that the line is above the original line if you increase your temperature. Likewise, if you had to decrease your temperature, then the line would have to be below it. So when you draw a change in temperature, then the curve should only cross once. Otherwise you've done something wrong, so double check that when you draw your Maxwell Boltzmann curve. Okay, the other point which is made on the slide is that as well as there being more successful collisions, there's also going to be more frequent collisions because the particles themselves will be moving faster and therefore they're more likely to collide. But this is the less important of the two factors. So the most important factor, the one that's really causing the increase in rate of reaction because you've increased the temperature, is this fact that a lot more of those molecules have now got the activation energy. So here's our lesson objectives again, which were to have a qualitative understanding of the Maxwell Boltzmann distribution of molecular energies in gases, to be able to draw and interpret distribution curves for different temperatures, and to understand how small temperature increases can lead to a large increase in rate. So as usual, have a look at these lesson objectives, make sure you understand them. If not, go back over the textbook or do some questions or do something to make sure that you understand this material before you come to lesson.